Hey math people. So projectile motion. Typically thought of in the physics classroom, however this is taught in the quadratics unit of a typical algebra or algebra 2 class. So in any quadratics unit you may find applications in it towards the end. Usually at about the second or third week mark, depending on how you teach quadratics, you'll introduce this equation in projectile motion. So the purpose of this video is to serve many purposes. One, it's to talk about kind of the problem with introducing this, but also the great advantages to it. To talk about why this is even a thing in the first place, how it comes to existence, because in a lot of cases kids are just told to memorize it without really understanding where it derives from. Talk about maybe the issue with deriving this in the first place. Really, you shouldn't derive this in the math classroom, which is a strange thing for me to say because I think deriving formulas and equations in the math classroom is critical for students to understand the background of it. But this one in particular, you maybe sorta shouldn't. Although there are sneak around ways to teaching this where you always give the student the formula needed for the projectile motion, and I don't think that's a good approach either. So it's a complicated science as a teacher to figure out how to introduce projectile motion because the derivation of this requires an understanding of physics and calculus. So imagine this, you're a freshman or sophomore in a regular math class, you know, you're just chilling, you really care about maybe what you're doing on a Friday rather than the derivation of the projectile motion formula for vertical motion, either perfectly upwards, perfectly downwards, or just being dropped. You're not really thinking about the derivation of this, you're more so thinking about, well, what do I need to do to make my teacher happy, to get that A? Oh, right, you plug in 9.8 meters per second squared for gravity, or 32 if you are using feet. And you plug in whatever the initial velocity is, so maybe you throw an object down at 10 meters per second, and maybe you're doing that from a 100-foot building. So you just plug in those three numbers, and maybe you're asked to solve for the maximum height, in which case find the vertex, or you're asked to find when it hits the ground, which is solving for a 0. That's good. That is great application of this formula, but there's an issue there. You're just doing some standard plug and chug stuff. So to some extent you are showing the students some great application of quadratics, which is very necessary in a room where you have 15-year-olds that are really questioning the purpose for math in the first place. However, real mathematics isn't just plug and chug. It's a lot more intuitive, it's a lot more problem solving, it should be a lot more open-ended than just plug in this, solve for that. So the struggle is real as a math teacher because what is the most effective way of showing this and teaching this? And there's a lot of other things to consider too. So imagine on the student's end, they're juggling this new concept of a quadratic when they were used to y is equal to mx plus b for days. What's my slope? What's my y-intercept? Not anymore. This is typically the quadratic, the first or second function in their arsenal of high school functions. So a bit of an overwhelming time as our high schoolers take that first step to, other functions outside of lines. So how do you properly show this? I'm not sure if there's a good answer. I usually talk about the general derivation of this formula and what each aspect of it means, but do I sit there and do the calculus necessary to prove the idea behind this? No. There are some worksheets that I found online as a teacher where this coefficient, actually sometimes all the coefficients in blue, are already plugged in for the student and they don't have to do any of that plug in aspect of the problem at all. They just have to typically just find the 0 in their calculator or find the max in their calculator, and that's all they have to do. I think that's robbing them of a little bit of the background understanding. There's a fine line, right? You don't show the calculus in physics, but you do talk about the concepts. I think that's an important aspect of it. So in a lot of cases, what kids will see typically in this coefficient is like a negative 16 or a negative 4.9, and I typically don't see these worksheets that I find online really talking about that all too much. Yeah, sometimes I take worksheets from the internet, okay? Is that a problem? Moving on. Let's talk about why. Let's talk about how. Let's talk about what this thing is and how we can even come to its existence in the first place. So we're going to hit a few birds with one stone here. This also will serve the purpose of introductory physics concepts. I'm not a physics teacher, but I know very minimal understanding of it. And intro calculus ideas, because ultimately the reason why most teachers don't talk about like this negative half here and why this turns into a negative 16 or negative 4.9. Well, the reason why a lot of teachers don't talk about that is because it requires that calculus. So I will use this as a tool to introduce an idea in calculus or a large picture in calculus without doing any calculus. So the challenge here is to not actually perform calculus. So I'm going to be a little creative. Hopefully you appreciate my creativity. So let's start with the most essential element of this entire equation, in my opinion, and that is this guy right here, the g. Okay, so gravity. This thing changes over time. At a very basic level, if I were to drop an object right now, it gets faster and faster and faster as it goes towards the ground. It accelerates. Its velocity is not constant, it changes with each passing second. So in a vacuum, not a literal vacuum, I just wanted to show this vacuum. I really like this vacuum. So in a vacuum just means without factoring in air resistance or anything like that. So generally speaking, objects fall at 32 feet per second squared. This is also 9.8 meters per second squared. What does that mean? It means that with each passing second, it gets 32 feet per second faster. So what we'll say here, we'll say that g is equal to negative 32 feet per second squared. So we put a negative in front because negative means we're going down, or positive would mean we're going up. I'm sticking with feet, but this is also the same thing for meters per second. We would just say negative 9.8 meters per second squared. So that's the thing about dropping an object. It has an initial velocity. The initial velocity is 0. I'm not applying any sort of force to it. But it's getting faster. That velocity is not constant. It's moving faster and faster and faster as it goes towards the ground. That's called acceleration. So we can actually call g a of t as a function. We can write this as a of t. So with each passing second, we are increasing our speed by 32 feet per second. So if we want to find the velocity at any given time, we would write this as v of t. We would need to do something with this gravity constant. In our case, in our world, using the units feet in seconds, it's negative 32. We need to do something to g, gravity. Well, when we're 1 second into our drop, we're dropping at 32 feet per second. If we're 2 seconds in, we're at 64 feet per second. We're just multiplying gravity by time. What we can actually do here is we can take that gravity and multiply it by our time, t. Here's the thing though, when you drop an object, sure, it had an initial velocity of 0. I didn't apply any sort of force going downward. But what if I were to throw the object up first and then let it pop back down? Or just shoved it down as fast as I could? That represents an initial velocity. So just because we have this idea here doesn't mean we can't also consider I additionally applied another force to it. The initial velocity, we call that v naught. So I'm going to add v sub 0, which means that initial force I apply, either upward or downward. We're not looking at angles because angles get way more complicated. That is not taught in the high school algebra setting. Okay, so we're almost there actually. Here we have this acceleration over time. Here we have now velocity over time. The projectile motion equation is its height over time. So we are at the last step here. The height over time is the last equation in this process. Now let's think about someone's height. It has to start at an initial position. So maybe it's from this 8-foot marker roughly, and I drop it from all the way up here. My hand's off the camera. But right around here, which is about 6.5 feet. That's an initial height, and then it falls, and then it changes over time, obviously. We need to consider an initial height first. But there are other things to consider when an object falls. Obviously, I can apply that initial velocity, like I said, and lastly, gravity. So we need those other two terms. So the velocity term is going to be pretty easy to play around with. Generally speaking, so I'll make a little side note here, distance is equal to rate times time, generally. And this is taught really early on. This is taught usually in middle school. So we can think of distance as height, and it's equal to the rate, aka the velocity in our case, times the time. We can loosely apply this idea to the velocity constant. We're going to have that initial velocity, which is v naught. And we're multiplying it by, well, with each passing second, time. But this is where it gets tricky. This final term is the term that I'm mostly talking about, and the critical moment of this entire video, the whole point of me doing this in the first place. What goes here? So what goes here is the need for the calculus. And without doing any actual calculus, I will be applying concepts of calculus, but without doing an actual calculus procedure here, I need to show some graphs. So I'm going to go hop onto Desmos here, and you'll see what I mean. Okay, so we are now in Desmos territory. One thing I want to really just quickly talk about is just the sign that I've been playing around with gravity. We're going to say that gravity is positive for the sake of this exploration. Just a side note, but obviously we have that negative coefficient in front when you're playing around with the actual formula. Anyway, moving onwards. So we have this idea of gravity, and we know that it's 32 feet per second squared. We can just calculate that. You can actually find that just through experimentation. It's a constant line. Right now we're looking at the graph of the gravity over time. So after 1 second, gravity is the same. After 2 seconds, gravity is still the same. 3 seconds, so on and so forth. It's the velocity that changes over time. It gets faster and faster and faster and ramps up in speed until it hits terminal velocity. And that is a whole nother concept I know very little about, but it gets faster over time. What we can actually do is we can borrow from this idea of calculus. It uses this fancy symbol. It's called the integral. We can actually integrate this line and figure out its accumulation over time. So what does that mean? It means I can find this area beneath the line. So what I can actually do is after I can find the area from, say, 0 seconds to 1 second. This is going to be that little formula for us. Okay, we're not going to do any of that math. In the first second, the area is 32. What does this mean? This means at second 1, at t is equal to 1, we'll have a velocity of 32 feet per second. And then we're going to start ramping up. So after the second, we're actually going to be at 64 feet per second. After the third, we're at 96, and so on and so forth. As you can see here, it gets bigger and bigger with each passing second. So by the 10th second, 320 feet per second is pretty fast. You don't want to be falling at that speed. I want to borrow this idea of area under the curve for the velocity function, and then maybe that will help us find that leading coefficient in our displacement, our height function. Okay, so now I'm playing around with the velocity function. I've changed this from g of t. I just chose g as gravity. It didn't take a because a is actually this lower bound here. I changed it to v of x now, and it's equal to 32x. It's the same thing we had in my board's over there. That's why I keep looking over there. It's the same thing we had in v of t. We had it equal to g times t, in which case we're doing the same exact idea. Note, remember, gravity does go down, but we're just looking at this area under the curve idea, and it's a lot easier when we're playing around with positive values. So let's think about that same area under the curve idea. Okay, so let's talk about what this line even represents a little bit. Right now our x-axis is seconds still, and our y-axis is now velocity. So with each passing second, our velocity is getting faster and faster. So at 1 second, we're at exactly 32 feet per second. After our second, which is a little off the graph here, I can kind of scroll to find it, we're at 64 feet per second, so on and so forth. So we get faster and faster and faster. It's going up and up and up. So if we want to talk about the area underneath this line, it's not going to be quite as simple as that flat line. It's not going to be just an increase of 32 with each second. It's going to be a little different. So let's explore this a bit. I'm going to look at our first second. So the area underneath this curve, you can actually try to figure out what this shape is. This shape's just a triangle. It's really easy to find this area without the need for this formula. Just like in the last case, it was a rectangle. This one is also a simple equation. In this case, we could just do half base times height. Base here is 1, height is 32. 1/2 base times height will get us 16. Half of 32 is 16. So in our first second, we're at 16, and if you are playing around with projectile motion, that's that magical number already. We're at 16 for our total accumulation, that total area underneath that curve. Now if we look for second marker 2, we're at 64, and very clearly here that's not a linear relationship. As time goes on, our position is not linear. It's getting faster and faster, so instead of it changing, say, 5 meters every second, it's not going to happen like that. It's going to change in a very different relationship. As of right now, we don't know what that relationship is. We saw that after the first second. Actually, we should probably be writing some of these down. I'll make a table here. At the first second, we were at 16. So what does this mean? We dropped 16 feet after the first second. After the second, we dropped 64 feet. Let's crank this up to 3, and actually we're getting pretty big here. If we crank this up to 3, we're at 144. So after the third second of falling, we are now 144 feet from our initial dropped location. For fun, let's just do one more. So looks like 256 for the fourth second. And as you can see here, this is very clearly ramping up pretty quickly, not in a linear fashion. We're actually done using this tool. This is called integration. You can actually see here, Desmos had a nice link to learning integrals. This is what we're doing right now. We're doing calculus, but not really. We're not doing the actual act of it. I'm actually going to remove all this integral stuff because we have what we need. Whoops, I needed that. We have what we need though. It's these points. How can we get that term? We need to figure out what this pattern is. So there's a few ways we can approach this. One thing I will say is that we know that this is quadratic because I already started with the equation, right? But it's also found in a quadratic unit in high school. So I know that this is going to be a quadratic term. There's quite a number of ways we can derive this. We can use regression. That's actually the fastest way. But let's pretend we didn't know that. How about we just play around with this change? So I know that parabolas behave in such a fashion. I know that, we'll just do 0, 1, 2, 3, 4. I know that we go from 0 to 1 to 4 to 9 to 16. And as you can see here, these black dots are filling in this curve. Let's think about the change here. To get from 0 to 1, we're adding 1. To get from 1 to 4, we're adding 3. To get from 4 to 9, we're adding 5. To get from 9 to 16, we're adding 7. So plus 1, plus 3, plus 5, plus 7. Over here with our green dots, if we take a look at what we're adding every time, it's a little different. Here we're adding 48. Here we're adding 80. Here we're adding 112. So I just jotted those numbers down. We can actually factor a common number between all these, and you might know what that number is based on the general formula for projectile motion. We can factor out a 16 from all these. So we're looking for that pattern of plus 1, plus 3, plus 5, plus 9, but we know that we're going to have some sort of coefficient in front because these numbers are very clearly not going up by those values. If we factor out a 16, if we divide out 48 by 16, we will get, I think, 3. If we do 80 divided by 16, that's 5. And if we do 112 divided by 16, that's 7. There's your pattern. We have that quadratic pattern, so x squared. In our case, we're using time, so t squared. And it looks like we're multiplying it by a factor of 16. So what we can do here is we can actually just write y is equal to 16x squared. We can see if that fits our curve. I'm actually done with the normal x squared now, and sure enough it does. 16, in our case, t squared. And remember, we're counting down is going negative and up is positive. It would be negative 16 t squared. Okay, so per the Desmos exploration, we can actually see, well, in our case where g is equal to negative 32, plop this over here. That's what this term would look like in the velocity equation. The calculus trick behind it, we ended up getting, what, negative 16 t squared. The calculus trick behind it is to take this power, which was a 1, and add 1 to it. What do you need to multiply this now 2 by to get negative 32 as this leading coefficient? So in this case, we did 2 times negative 16 to get that negative 32. So generally speaking, let's just say we didn't want to use 32 feet per second squared for gravity. Let's just say we wanted to use this 9.8. We would actually just write this as negative 1/2 g times t squared. The reason why, you'll notice what we technically just did was we took that gravity constant and we cut it in half in order to get that coefficient, which brings us to the equation we started with in the first place. This, ladies and gentlemen, is the reason why we end up using this h of t is equal to negative 1/2 g gravity times t squared plus the initial velocity times time plus the initial height. This is our projectile motion equation. We show 15-year-old students roughly without really digging deep into the background of the physics and the calculus for your own good, but it's sometimes nice to know and see what's actually going on in the background. I'm going to ask you to continue to math on, and I will do the same. I'll see you in the next video.